Hello all. Today I'm going to be talking about combinatorics in math. So basically, combinatorics is a branch of mathematics where we study enumeration, combination, and permutation of sets of elements, like numbers, for example, and their relations that characterize like their properties, like characteristics. Um, Besides computer science, combinatorics has other applications in other fields, such as mathematical optimization, ergodic theory, and statistical physics. There are many subfields of combinatorics, but today I want to focus on enumerative combinatorics, the counting aspect. So basically, enumerative combinatorics, we count the number of certain combinatorial objects such as numbers and sets and such. There's this example called the Catalan numbers example that I'll be going over through later on. But right now, I want to talk about the other combinatorics, which is includes analytic. It's like enumerative, but it uses techniques of counting the objects to derive formulas. It also uses complex analysis techniques to derive asymptotics. Another one is partition theory. So, like in number theory, partition integers like so. Here we have the number 15, and we partition it in five ways: 6 plus 3 plus 3 plus 2 plus 1. We could partition it a finite number of ways. Another way we could do it, partition it in seven ways, where we would have 3 plus 3 plus 3 plus 3 plus 2 plus 1. That'll equal 15. Uh, Another one is graph theory, study of graphs, which are ordered pairs, vertices and edges. Here in this picture, we have a weighted graph. Another one, combinatorial design. That's the theory about where we want a construction of finite sets to be arranged symmetrically or balanced. Here in this picture, we have the plane. As you can see, it's pretty perfectly balanced. Finite geometry. That's where like the system has a finite number of points. So for in this picture, we have a affine plane of order 3, meaning we have three points connected with the lines. I think there are 12 lines here and 9 points. And the connections don't overlap because we only want to connect 3. And that's our finite affine plane. Order theory, that's where we have binary relations, where we want to explore the notion of order. So, like a formal way of writing things, such as this is less than that, and so forth. Matroid theory. This is the study of finite sets in the vector space. So, like matroids could be an independent set. They could be bases and circuits. Closed set. They have a lot of names for matroids. A lot of ways you can characterize a matroid. In this example, it's called the Vamos matroid from graph theory, and it cannot be represented as a matrix over any field. Extremal combinatorics. This deals with sets and how large they have to be. Like if they have any restrictions of such. This includes like numbers, graphs, vectors, sets, etc. Probabilistic combinatorics. This is where we deal with statistics with random objects. It uses the probabilistic method to solve answers in graph theory, number theory, analysis, and computer science, etc. It's a pretty new field. Here we have geometric combinatorics. That's where we have the study of convex and discrete geometry. We count the faces of the polyhedra. And this is a picture of a polygonal model. We have also algebraic combinatorics. This one just deals with abstract algebra. It's a new one, along with probabilistic combinatorics, like I mentioned earlier, and combinatorics on words. And that's another one, combinatorics on words. It's a formal way of interpreting words and formal languages. Um, like it focuses on things like patterns and repetition with words. We could use numbers to represent the words. Topological combinatorics. This one is like methods in topology, where we we talk about graph coloring, fair division, partitions, the partially ordered sets, the decision trees, and the necklace problems, such as this one, for example. So like the necklace problem is where, let's say you and me, we rob a bank, we steal a necklace. I don't know why a necklace would be in a bank, but we want to split this necklace evenly because these rubies and emeralds aren't valued the same. So we want to not waste as much material when we cut the metals. So we need to find a way to partition it. Arithmetic combinatorics, that's where we have the estimates in the arithmetic of sets. Enumerative combinatorics is the one I wanted to talk about, and I wanted to talk about specifically the Catalan numbers. So the Catalan numbers is basically something not to be confused for the Catalan language in Spain. It was basically founded by a Belgian mathematician. His name is Eugene Charles Catalan. And what they are is basically a natural sequence of numbers that you see, like in problems everywhere. They're usually recursive. There's another one that we see, like the patterns and shells that we see with like the fractals. The Catalan numbers is something like that, something that we can use. And so here we go. We start with C subscript n, where n is could be any number greater than zero, greater than or equal to zero. We use binomials. And as you can see in this equation, we get 1 over n plus 1, and then we take the binomial 2n and then over n. We get 2n factorial over n plus 1 factorial times n factorial. And then we get this little nice equation. So like the first Catalan numbers for n equals 0, 1, 2, 3, etc. would be 1, starting from with 0, 1, 2, 5, 14, 42, 132, etc. So say we use 2, we would just plug it in. 2 times 2 is 4, 4 factorial is 24, over 2 plus 1 factorial, which is 3 factorial, which is 6. 6 times 2, we would get 12. So 24 over 12 is 2. Here we have, we use 5. So we have 5 nodes that we partition. We don't want them to intersect. So we get basically like a power set. And so if we look back here, 5 is 42. So we get 42 non-crossing partitions when there are 5 elements. And we get 10 that we don't use because they cross. Applications of the Catalan numbers that we can use is something like the mountain ranges. So here we have C subscript n is the number of ways to form a mountain ranges with n upstrokes and n downstrokes that all stay above the original line. The mountain range interpretation is that the mountains will never go below the horizon. So when we have 0, we have just one way. When we have n equals 1, we have one way as well. We just have the forward slash backslash. And then when we have n equals 2, we have two ways. We could either have the two little ones or we could have that one big one. And then when we have n equals 3, we have 5 ways. And so we have the first one with the 3, the second one with the small one and the big one, the third one with the mirror of that. The fourth one is the interesting one. So using a binary operator, so like a binary tree, such as a full tree, we can find the Catalan number in the full binary tree. So like let's say we wanted 3. Here are my poorly drawn trees with 3 nodes in each. So what we want to do is we add leaves to these nodes to make the whole tree full. So like for the first one, we add 2 to the bottommost node, and then the one on the parent, we add one more to make it full, and then the very root one, we add one to make it full as well, and we end up getting four leaves. Yeah, n plus 1. 3 plus 1, we get the 4 leaves. No matter how we create the tree, we're always going to get the 4 leaves. And this is true for if n was 5, 6, 7, 8, with the really big numbers. And then finally, last example, C subscript n is the number of different ways a convex polygon with n plus 2 sides can be cut, like into triangles, by connecting the vertices with the straight lines, and we don't want them to intersect. The following hexagons, we use n equals 4, and we should get 14 different hexagons that have differing triangles. Some of them are mirrored and some of them are not. But looking back, if we remember the Catalan numbers, when n equals 4, we should get 14. So yeah, there you have it.